and a friend of many years, talking about invariant theory.
Okay, thank you. I would like to thank the organizers for the kind invitation to be here and to be able to talk here. The plan of my talk is to give you a short introduction into some aspects of invariant theory, and in the second part I try to show an application to liquid crystals, which is based on joint work with David and Stefano. Okay, so the first point is showing some general remarks, and then we go to the invariant theory, and at the end we go to the application. So we have a group. In general, my groups are finite or compact Lie groups, and if you want, you can think about SO3 or O3. These are also my favorite groups for a long time. Then I have a linear space, which has an inner product, I should say, because in one of my last talks somebody reminded me that I need an inner product for the things to follow, so I just remarked it at the beginning. And I have a group. My group acts linearly on V. It means I have a group homomorphism from my group T to O of V, which is the orthogonal maps from V to V. And we are interested in invariant objects. What do I mean by that? By this, I mean functions which are invariant under the action of the group, which takes the same value along the group orbit, or equivariant vector fields. I mean vector fields. So I changed notation. V should be here, and this should be a point in my space which should be different from the vector field, and this should be a V. Sorry for that. It's always dangerous to change notation. You could also think about tensor fields, which where you require a certain transformation behavior. You can think about director fields, which take values in the real projective space and where you act on it by an action like this here. So we are interested in invariant objects, and this calls for invariant theory. The questions which will be asked in applications are existence of or number of minima, maxima, critical points for invariant functions, or equilibria, stability, bifurcations for vector fields, or maybe dynamics. So these are the questions which are behind, but we will not touch them in my tutorial on invariant theory. Why does symmetry help you in the analysis of these equations? There are 2 points to that. One is you have geometric restrictions on your phase space, which come from invariance properties by fixed point spaces of subgroups. So this is what we have seen yesterday in Pascal's talk, where he used the equivariant branching lemma, and this lives on these restrictions. So I will not really emphasize this. I will go on the second part, where we have fewer terms in the Taylor expansion of these functions. And I would like to make clear what it means that we have fewer terms. Let me make a remark which was already in Pascal's talk yesterday. If we have a closed subgroup of G, we denote by the fixed space of H the elements in V which are fixed under H, and the dimension of the fixed space. And I think this was not given in your talk yesterday. The dimension of the fixed space is given by the number of times the trivial representation of H is contained in the representation of G. So this is a way of counting the representations, and you do this by restricting the character of the original representation to H, and you integrate this character over H, and the integration, if you do it in general, you use Haar measure. If you have a finite group, you just add these values. So this is a very general formula to find out the dimension of the fixed point space, and you will see why this is useful later. So we are interested in the number of such objects as we have seen invariant functions and so on. And so in general, the answer is infinitely many. So this is not really helpful. So one has to ask this question a little bit more precisely. So the next question could be, what is the dimension of these objects? I mean, they form vector spaces, and you can ask what is the dimension. But still, in general, this answer is infinite, and you need a still more precise question. So what I do need is a notion of smoothness, and this also needs, in principle, a formulation in function spaces, as we have seen in the talk by John Ball earlier this week. So this would be the appropriate setting here. I assume all objects are C infinity, and one general result is the following. If we take any C infinity vector field, which is equivariant under my group, I find numbers S and R in N, and functions which are in C infinity on R to the R, which is this number here, so that we can write our equivariant vector field as a sum of vector fields. I mean, the EIs are homogeneous equivariant polynomial maps, and these are S such vector fields, and Fj depends on R functions which are invariant. And any vector field can be rewritten in this form. And so the natural question is to ask, what are these numbers R and S, and what are these functions pi1 to pi r, and what are these polynomial vector fields EI? And how many do we have? We could also ask for other invariant functions, like, for example, in the Sobolev spaces, and I have not seen any answer to similar questions in function spaces of non-smooth functions. For example, if you look at WKP, you could ask what are the invariant functions in these functions, and you could conjecture that you can write it as in a similar way as a function in WKP on the orbit space of this in the same functions here, but I'm not sure whether this is true. So the question is, what is the dimension of the space of homogeneous invariant polynomials of fixed degree? So this is what we call invariant theory, and what is the number S and R, and so on. For this we denote by PD the space of invariant polynomials from my space V to R, which are polynomials homogeneous and of degree D. And in a similar way, I write MD VV, the space of homogeneous polynomials maps from V to V, which are of degree D as well. I mean, this D is always the degree of these polynomials. And with this, we set C of D is the dimension of P of D for the if F is invariant, and E of D is this dimension of the equivariant vector fields homogeneous and of degree D. And what we ask for is for a formula for these dimensions. And this is a theorem which is due to Moline, and he lived from 1861 to 1941. He is a Baltic mathematician who published in German, and by the way, for those who are interested, he was a very strong chess player. So he did the following. You write down a series where you write the coefficients CD, you introduce a dummy variable lambda, and so you look at this series CD lambda to CD. And for this series, I write R, G, V, lambda. The R is because these functions form a ring. For those who are interested in some algebra, and this is a representation space, this is my group, and this is a dummy variable. And the surprising thing that this is equal to the integral on the right-hand side. I take the determinant of 1 minus lambda, which is the same variable here, times my rho of G, and integrate over G with respect to H measure, and I get a representation of this series. So if I can compute this integral, I get all these dimensions somehow out of this. And similarly, if I want to define the dimension of the equivariant vector fields, I write the series ED lambda D, and again the summation, And now we get this similar formula, but we get a trace of rho of g in the numerator of this integral. So in some sense, I think this is a very surprising formula. When I first saw it, I found it hard to believe, but one can prove it, in fact, and I prove it to you. Not really. I mean, I show you what one has to do to prove it. We have an action of G on V, and this action of G on V induces an action on all kinds of objects like functions, vector fields, whatever you like. And so you do this by acting on the variable with rho of G inverse. So you have this new action on your objects by doing this. And you do this on function polynomial maps and so on. And then you ask for those which are, so you have an action on this, and you ask what is the dimension of the fixed point space in these representations. So if I find the fixed point space for G in the invariant polynomials, then I know. I mean, if I find the dimension, I find these numbers which I had before. So I do the character formula which I had written down for G on these objects, and this is some computation. I mean, this is not complicated. You just have to do it. And so if you see the proof, it's in fact not very complicated. It's a long computation, but it does not really fit to the surprising theorem which we have seen. Let me do some examples. If we look at the Alice-2 representation of SO3, I choose it because we have seen it many times before this week. Then the Moline series for the invariant polynomials is given by this object here, 1 over 1 minus lambda squared times 1 minus lambda cubed. And if you look at the Moline series for the equivariant vector fields, you get the same denominator, and in the numerator you get lambda plus lambda squared. So what does it tell us? It tells us that we get two algebraically independent generators for the algebra of invariant functions, and we get two generators of the module of equivariant polynomial vector fields over this ring, and we can write the C infinity functions in the form I have given before with these elements. And if we write down a map Q from a map pi, where we map Q to pi1 of Q and pi2 of Q, because it's a Hilbert map, and the image of this vector space V2 under this Hilbert map is a homeomorphic image of the set of orbits of our group, and so this is what we call the orbit space. And you can reduce differential equations on the orbit space, and this is true for all groups. I mean, this in this case, you have a five-dimensional space. You have a five-dimensional representation space, and the differential equations would go to a two-dimensional object in the orbit space. This is similar to what Pascal has shown yesterday, but he has used a different reduction using the geometric feature, and this is a invariant theory feature. But this Alice-2 representation is so special, so many things work which would not work in general. The Alice-2 representation is on the 3x3 symmetric matrices. Yes. This is one way of putting it, and this is why I wrote Q here. And from this you can determine the invariant functions, which are trace of Q squared and the determinant of Q, and the determinant. I asked this qubits questions earlier this week, but here you have the explicit formula. The determinant of Q is 1/3 times trace of Q cubed, and so in this case, of course, where you use the traceless property, and so you get this information. And for the equivariant vector fields, you get the vector fields Q goes to Q and Q goes to Q cubed minus 1/3 trace Q squared q squared minus 1/3 trace of q squared times the identity. So this is the complete analysis in some sense of the LS2 case. One observation one should make: they are non-gradient equivariant vector fields. Also, this might look, I mean, if you look at this, you see you have two generators for the equivariant maps, and you have two generators for the invariant functions. And so you take gradients and you think all of it is gradient, but this is not true in higher order. If you go up to higher order, you lose gradient property. It's getting much more complicated.
Yes. Is there any proof that the series for characters can always be presented in terms of 1 over, you know?
You see, these formulas, they are very general, in fact. The numerator need not be 1 in general.
No, yeah, of course.
But you can always get a form like this.
Irrespective of, that's for compact groups.
Compact groups, finite groups, whatever you like. But it is a non-trivial task to compute the series in general. I mean, for this case, it is not so complicated, but if you take L is whatever you like, then it's getting much more difficult. But one can do it.
And there is a proof that this form can always be reduced.
There's a proof for this, yes.
For finite groups. For Lie groups,
for Lie groups is a little bit, yeah.
Yeah, but
the work of Patera and Winkelnitz, for instance, they gave it for L7.5.
I mean, David and I, we have a long going discussion whether this is a general fact or not. So we can go into this. But besides the proof, there's an experience that it always works. But it could be very difficult. And I mean, the final goal of my talk is to show you an example where it's highly non-trivial to compute the Moline series and where we have succeeded to do it. This will be, so to speak, the highlight at the end of the talk, if I get there. Okay. This we have seen already. Okay. So what I wanted to show you as a very short remark, and I want to use some is there a non-trivial piece of chalk somewhere?
Here.
Yeah. The orbit space. I mean, I had this on the screen before. We have this map pi from V2 to R2, and the image of our orbit, the set of orbits looks like the following. We have here the variable pi1, which is non-negative, and we have in this direction pi2, and the orbit space looks like this. There's a cusp here, and like this symmetric up and down, and so if you fix a norm, pi1 is more or less a norm. So you fix a norm. This is a sphere in your space, and these points up here are the ones with higher isotropy, and these are the points with higher isotropy, and in between you have the points with general isotropy, and the equivariant branching lemma gives you bifurcation onto this set, but it's not clear whether you get bifurcation into the interior of the space. That would be a secondary bifurcation, which could happen under certain assumptions, but I also would not know, maybe you know, what it means for the liquid crystals to have bifurcations into the interior of the space. But this no, yeah, I don't see this, but maybe you're right. He's almost always right. So maybe one further remark. Sometimes it's really difficult to compute the Moline series, and there is a formula which was published by David Selinger in '79, and Paul Matthews pointed out to me that such a formula exists. I had overlooked this formula. So you can directly compute the dimension for, I mean, you fix a degree and you compute the dimension for these spaces directly. And how do you do this? You introduce this term chi sub d. Chi is the character, and this is something derived from the character, and so you get CD, the dimension of the invariant polynomials, space of invariant polynomials of degree d. And so what is chi of d? It is this expression. So you take your original character and you take d tuples of non-negative integers where you multiply ij by j and you add them up to d, and you take all these and you look at this expression and you integrate this expression. This looks horribly complicated, I find, and there's a slight simplification if you use integer partitions. So if you take an integer and you look at the partitions of this integer in sums of non-negative integers, this is a theory which is or a topic which is very hot in number theory, and this is an extremely fast growing sequence if you look at the number of partitions of given d. But if we take it to partition, we take this summons d1 to d2, and this are the multiplicities, and then we get chi of d in this form where you add over all the partitions and you look at this term in form depending on these numbers occurring in the partitions. And for this, also one example, if you look at chi 2 of g, you get this nice formula. And if you, for example, look at chi 8 of g, you get these terms which you have to add. And these are 22 terms, and I left out some of them because it did not fit on the screen. So this is a very nice formula, and it's very effective for finite groups. I have not tried to use it for infinite groups, but for finite groups, this is a very effective formula. So let me approach the application to liquid crystals. We first go through a number of slides which you probably know everything about. I don't know so much about, and David was friendly enough to produce these transparencies for me. So we have a liquid crystal which has orientation and position. The molecules have orientation and position, and they interact, and we have an equilibrium state. We are interested in phase transitions, and we want to study these phase transitions using bifurcation theory. So we use a free energy which is defined on a space of order parameters, and these should measure the alignment of the molecules. So we have seen a lot of discussions this week, so I don't want to add to this. I should not even dare to touch this topic. And the basis is a molecular field theory which was published by these authors, and David acknowledges many discussions with Slukin, and I acknowledge some discussions and evening meets with him as well. And we refer to this as a KKLS methodology. And so we have quantities Q1 to Qn, and they are supposed to describe these properties which are of interest to us. And we have an element in SO3 which describes the orientation of the molecule, and with respect to a fixed reference configuration. So we assume that G induces a linear transformation on this Q1 to Qn, and so we have a representation which has this property, as we had in the very beginning of my talk, which is now a map from SO3 to a general linear group over R, and of course we, by the same method as I did not mention in the beginning, you can assume that this is in the orthogonal group on the space. We have some assumptions on the molecule, and so we take probability density function on SO3 which takes values in 0, 1, This is a ensemble average for F, and again dg is a Hermitian. Then we have the entropy. I think this is also a well-known quantity in this environment here. And we look at a term f of g in the form z eta to the -1 times e to the eta times rho of g, where this means this kind of scalar product. And this is normalizing so that the integral turns out to be 1, because this is the integral here. And so we look at the w of eta in this form, which takes this shape, and we have an entropy having this shape here. And I think we have seen all these formulas earlier in the week in several talks. And then we have the free energy finally in this form. T is the temperature, and the stable phases are minima of the free energy. So this is in very short the background, which is more familiar to everybody else here than to me. So we look at the natural symmetries of the free energy. So we claim that the partition function is invariant under the multiplication with A, where A is an element of GLNR from the left, and we also have that this is invariant under the transposition or taking the dual in GLNR. And the proof is very easy. If you look at this, we act on Z by rho of H. So rho of H goes into this, where we take the scalar product here. And this means that we put it on the other side with a transposed. And now this is an element of SO3, and by the properties of Hermitian, which is invariant under left multiplication, this is not changed, and so we have the invariance properties of this function. And similarly for the transposed, we take the transposed here, it goes here, it goes here, and then this is the same because this is the integral over rho g inverse, and again this is a compact group, and in the compact group the Hermitian has a property that these things are equal, and so we have invariance with respect to this left action and with respect to the taking the transpose. The ensemble average is as a consequence also equivariant with respect to the symmetries which we have described, and the same is true for the entropy function. If we look at this group now, which is generated by the symmetries given in I and 2I, I mean which were the left multiplication and the transposition, we see that we get a Rees product of SO3 with Z2, and which, if you write it out, you get SO3 times SO3 semi-direct product with Z2, or you can also describe it in matrices. You have matrices Mn in SO3, and you have tau epsilon, where tau epsilon squared is 1. It's one of the properties of the transposition. And if you apply tau to Mn, you do this, which is also very natural. So we have an action of this group on the space of n by n matrices given by rho tilde, where rho tilde does the following: it multiplies A from the left with M, from the right with N transposed, and if you apply it to tau, it goes to the transposed of A. So we have this group acting on GLN, and the next step is when n is 3, GLN is 3, then Mark Roberts and Esmeralda Sousa Diaz have pointed out that invariance under tau is automatic. However, in general, this is not the case. I mean, if you have these symmetries, it's not clear. The SO3 symmetry SO3 times SO3 symmetry, it's not clear that you have automatically invariance under tau. This is also remarked that it seems that this has not been really observed in the literature, but I'm not a specialist in the literature, so I would not swear on this. If we assume that the molecules are biaxial, yeah, this is what we assume, and the order parameters are quadratic forms in R3, which are represented by 3 by 3 matrices, and I mean, we have seen this before, and of course Q is 0 corresponds to the isotropic state. If our space is V is in R5, the space of symmetric traceless 3 by 3 matrices with this action, and if we do have these two symmetries, then we act with our group SO3 with Z2 on the space R25, which is equal to the group of the general linear group in 5 dimensions. So the elements of V are already matrices or tensors. So some people call these objects we are dealing with supertensors. And so the program to study this would be find a Hilbert basis for these functions, expand the free energy, use singularity theory, do a bifurcation analysis, and describe the possible phase transition. So this would be the whole project. The question is, can we do this? We started to compute the Moline series for this action, which is the very first step that we know how many functions we have to deal with and so on. So this is maybe the step which would be here before the first step, because the Hilbert basis is the first step after you know how many you have. Yeah, it's a program. We remember this is a formal power series in a dummy variable, and for the linearly independent G-invariant homogeneous polynomials, and so we have to compute the Moline integral, which I denote by R SO3 times Z2, and here there should be this space of this 25-dimensional space. I did not write it down, and this is the integral we have to work out. Now this group is 6-dimensional, and the space on which it acts is 25-dimensional. So we should get in the denominator a product which looks like the one which we had before in the LS2 case, but the number of factors should be 25 minus 6 equals 19. This is what general theory would tell us. This is a first check whether the computation is correct, that we have 19 factors in the denominator. So the theorem is that we have done it, and the answer is partially given by this slide here. The denominator is given here, and if you add these exponents of these formulas, you will see that they add up to 19. So the first check is looking good, and it has the form which you wanted to see, even in this case. And we have a numerator which starts with 1, 2 times t to the 5, and so on, and ends somewhere. There's a bracket which should not be there, but with a t to the 104. So there are, and you see these huge numbers here. There are extremely many invariant functions which are needed to generate this. So it's probably not feasible to compute them all and to base a theory on the knowledge of all of these. So there should be something done which is not relying on all this information. So the Moline series, if you expand all this, you get an Moline series which starts like this here. And so the interpretation is you get 1 degree 0 invariant. Okay, this is a function 1. No linear invariance, which is also clear. 1 quadratic invariant, which we know, and so on. This is what we can conclude from this here. Yeah?
You have 1 minus 2 to the power 4 and all that to the power 3.
Yes.
What does power 3 mean?
Power 3 mean, I mean, the interpretation of the denominator is that these are algebraically independent invariants. So you get 3 quartic invariants independent invariants. Yes, I mean all these 19 are algebraically independent, which means you cannot write down a polynomial in 19 variables which vanishes in all these invariants which you get.
And numerator means that they only appear linearly, right?
Yes, numerator means that they only appear linearly. But this is not clear whether, our discussion sometimes goes in this, whether this is a theorem, whether this is really linear. I mean, it should be algebraic dependent, but whether this dependence is on quadratic level, I have not seen, I think it's true, but I have not seen a proof of this. But again, it's experience. Whenever you compute it, it's linear. Okay. There should be a proof, but okay. So this is what you can conclude from here. If we take SO3 times SO3 without the transposition, you see that the series looks very much the same, but there is a slight difference here between 4 and 5 in degree 4, and then this gets more in degree 6. You don't see a difference in the lowest order invariance between the group with or without transposition. Okay, my time is almost up, but one could try. You have seen this yesterday in Pascal's talk, that he reduced to the two-dimensional space, and of course one could do a similar procedure here. And the question is that we can get a rigorous reduction to a lower dimensional space on which the computations are more feasible. And for this, we have to do some more work. And with this, I thank you for your attention.
Any questions?
Reiner, you wrote in a previous slide that there is 1 cubic invariant that but you don't understand it.
Mm-hmm.
Why?
You want to say?
Sorry, did you say that again?
There is one cubic invariant,
Yeah.
and on the slide it's written, but we don't understand it.
yeah.
So why do you not?
Well, it's not clear what it means. I mean, it probably is known to physicists in quantum mechanics, but it's not clear to us what it. We have an algebraic expression, but we don't have a feeling for what it actually represents.
Mm-hmm.
Thanks for helping out.
Yeah. So I'm trying to translate into what I know about these problems. And if I look at either some second moment tensor equation that's got all the symmetries of the Smolyankovsky equation, or even that equation, where for equilibria, you can basically reduce everything to the second moment by the Boltzmann form of the Boltzmann distribution. But let's just look at the tensor equation that has these symmetries. Mm-hmm. What we do is since we know it's rotationally invariant, we mod out by the orthogonal frame of the tensor. Okay. Reduce the dynamics to 2-order parameters. So somehow, and then you can write down the solutions. You can look at that.
You are in Alice too.
Yes. And
yes.
And so you can look at the dynamics in a little triangle that's bounded by the the bounds of those order parameters.
Yes.
And so I'd love to be able to see how all of these invariants you're computing are related to the solution space of those equations. What a lot of things have to do with the boundaries, special symmetries that reduce us along, axes in that order parameter space. But maybe that would help to give some insight into what all these invariants are. There's something special about the dynamics in that reduced space and all these invariants that you're computing, I think.
I mean, if you do what you described, that you take a subset of your space where you, so to speak, mod out the action, then you should have singularities at the edge of your set. And you see it here. I mean, this space. This is let's say a true reduction. I mean, there nothing special should happen, but still you have this boundary which is singular in some sense. But if you
those boundaries we get look different.
They look different, sure, yes.
They are your boundaries.
But then you should have other singularities near. I mean, if you write down the differential equation on this space, you should introduce boundary effects. I think this is very natural, which should not be here, but in principle, this equation which you get here does not extend beyond these lines, and so this is, I think, geometrically the right reduction. Maybe we can talk about this later.
There was a point that I was confused. When you talked of the theory of symmetry, some slides before, I could see only the orientational part. Do you also take care of the translational group? And if so, have you done a theory also for biaxial symmetrics when you have a combination and not necessarily independence of the positional part and the orientational part?
I think we don't have any translation.
We have no translation.
So it's not really a symmetric. It's
I think I did not mention symmetric in my talk. At least I don't recall.
Go back some slide. Maybe I understood my confusion.
Okay.
When you quoted the factorial team looking theory, I thought you had some.
Clearly, it can be done because it's a space group representation.
Yes. First is the one where you quoted Catriel-Lackert.
Okay. So we have to
I
go.
thought that paper was for symmetric, but I mean, it's clear what you mean anyway now.
The second paper was on.
Here is this paper.
Okay.
That's pneumatic.
That's pneumatic.
That's definitely pneumatic.
I think they
But
describe
you could do it.
describe the general framework and then they specialize too. So yeah, great. Yeah.
Can I give you some more headaches? So now you're looking at interesting things that happen within this system with these symmetries.
Yes.
But I would like to perturb the system and spontaneously break that symmetry group and create another symmetry group.
Okay.
That's very different. And what's known about if I now I break this symmetry and what survives under perturbation is a reflection symmetry.
Okay.
What's known about how invariant sets perturb under such perturbations? This is related to what happens instead of having groups of equilibria. What happens is that curves and points survive.
In fact, I have looked at similar problems in different contexts, not with these groups, and I think it depends on the groups. I mean, it depends on the original group and on the symmetry group which you remain in your perturbations. I mean, you choose something, and then there's a certain technology to compute the objects which will survive. This is an algebraic technology to describe it, and it depends on the case. But the dynamics can be very interesting. I mean, there can be very interesting dynamic effects coming out of this.
We actually know the dynamics. That's why we like to give you the answer, and then you guys prove it.
Yeah. Can discuss this.
And gals.
I think we should press on. Thank you very much.